For this question, we want to find the derivative of the function y equals negative 2x to the negative 2. And the technique that we're going to use to find this derivative is logarithmic differentiation. I'm going to take the log on both sides of the equation. And the reason why taking the log of both sides is a good idea is because this introduces the log properties and allows me to simplify the right-hand side. We have rules for calculating derivatives when we have x to a power and when we have a base to the x power. But we don't have any derivative rules for when x is in the base and x is in the exponent. So calculating the derivative with logarithmic differentiation allows us to get that x out of the exponent. Okay, so I'm going to revise this problem and remove the negative. Okay, and so we're going to now use the log properties to simplify the right-hand side. And one of the properties is called the product rule for logarithms. And the product rule for logarithms says that if you have a product inside the log, that's multiplication, which we have here, then you can write this as natural log of 2 plus natural log of x to the 2x. So when you have a product inside the log, those factors get their own log and you separate that with a sum. So that's the product rule for logarithms. And then you're going to be able to use the power rule for logarithms. This logarithm on the right has x to a power. And the power rule allows you to move that power to become the coefficient of the log. Now, as I was looking at your work on some of these problems, a very common mistake that students made was on this step right here. Students tried to apply the power rule on this step. So that would, if you tried to apply the power rule, you would move that power in front of the log and get something like this. So when you have, I want to talk about the reason why this is an incorrect step. So when you have a coefficient inside that log, or sorry, a coefficient on the front of that log, that whole thing is the power on what's inside the logarithm. And you can see that by our statement here, this 2x is only attached to the x. So if I move it in front of the log right now, we're saying that that 2x is the power for both of these, and it's not. So that's why I needed to do this step where I separate out the two factors and then apply the power rule, because that 2x is the power only on that x. Okay, so now that we've got that common mistake out of the way, we'll continue to solve this problem using logarithmic differentiation. So I've simplified with the algebra properties, and now I'll calculate the derivative with respect to x on the left and the derivative with respect to x on the right. On the left, we're taking the derivative of natural log, and the derivative rule for natural log is u prime over u, or the inside of the log, sorry, the derivative of the inside of the log over the inside. So that's y prime over y. On the right-hand side, this is natural log of 2, which is a constant. There are no variables in that expression, so the derivative of that constant is 0. And then for the derivative on this part, we need to use the product rule because we have a variable in this first factor of 2x and a variable in the second factor of x. So we'll use the product rule to calculate that derivative. We'll do the first times the derivative of the second plus the second times the derivative of the first. We have y prime over y equals 2x. The derivative of natural log x is 1 over x. The derivative of the inside is 1. The derivative of x is 1 over the inside. And then natural log x times the derivative of 2x, and that's 2. We have y prime over y. And if we simplify, our x's cancel, so we have 2 plus 2 natural log x. My goal was to find the derivative of y, the function y. So I'll multiply both sides by this denominator of y. So I have y prime equals y, and y is the original function. So our original function was 2 times x to the 2x. That's 2 times x to the 2x times our 2 plus 2 natural log x. So we now have the derivative of our function. So the original function was 2 times x to the 2x, and we found the derivative to be 2x to the 2x times 2 plus natural log x. I just wanted to make a correction. I left off this 2 here. So we have 2 times x to the 2x multiplied by 2 plus 2 natural log x. For this question, we want to determine whether the mean value theorem can be applied. If it can, we want to find all values of c guaranteed by the theorem. So we have the function f of x equals 3x minus x squared on the interval from 2 to 3. I want to pull up the statement of the mean value theorem. The mean value theorem states, if f is continuous on the closed interval a to b and differentiable on the open interval from a to b, then there exists a number c in AB such that f prime at c equals f of b minus f of a over b minus a. So this is the conclusion of the theorem, and the symbols don't seem quite as dramatic as what those symbols actually mean. So let me just remind you that this left-hand side of the statement, the derivative at a particular value is referring to the slope of the tangent line. At some value c. And the right-hand side of this statement, f of b minus f of a over b minus a, is referring to the slope of the secant line. And we're saying that as long as you have a continuous function and a differentiable function, then we're going to be able to find this value of C. This value of C is somewhere inside the interval where that slope, the slope at that point, matches the slope of the secant line. So first we want to think about whether the mean value theorem can be applied for this particular function on this interval. So our function f is 3x minus x squared. That's a polynomial function, and a polynomial function is continuous from negative infinity to infinity, so certainly it will be continuous on the interval from 2 to 3. So because f is a polynomial, f is continuous on the closed interval from 2 to 3. In addition, the derivative, the next condition is that our function needs to be differentiable. Our derivative will also be defined over all real numbers because f is a polynomial. And so f is differentiable on the open interval from 2 to 3. So just typically, if you're thinking about functions that might not be differentiable, those are functions like the absolute value function. If you think about that graph, this is a function that is continuous, but because it has a corner in the graph, the function is not differentiable at that corner. You also have some radicals that create a cusp, and the function would not be differentiable at that cusp. So those are just some basic cases where a function might be defined but not differentiable, continuous but not differentiable. But for polynomial functions, they are continuous over all real numbers and differentiable over all real numbers. So we have met the two conditions of this theorem, f being continuous and differentiable. So we have the conclusion, there exists a C in the interval from A to B such that this statement is true. So we know that there exists a C on the interval from 2 to 3 such that the derivative at C is equal to f of B minus f of A over B minus A. So we have determined that this theorem can be applied, and then we want to find the value of C guaranteed by this theorem. So to find the value of C, we need to calculate this right-hand side of the statement. Then we'll calculate the derivative of the function, and then we're going to create an equation and be able to solve for that value of C. So let's calculate f of B. F of B would be f of 3. That's 3 times 3 minus 3 squared. That's 0. F of 2. That's 3 times 2 minus 2 squared. That's 6 minus 4, which is 2. So if we're calculating f of 3 minus f of 2 over 3 minus 2, that's 0 minus 2 over 3 minus 1. I'm sorry, 3 minus 2. That's negative 2 over 1, which is negative 2. So the right-hand side of our statement works out to be negative 2. And we'll start calculating the left-hand side. That's the derivative of f. Remember, our function f is 3x minus x squared. And the derivative of that will be 3 minus 2x. So then we're going to create our equation. The left-hand side of the equation is the derivative, and the right-hand side of the equation was that f of b minus f of a over b minus a, and we got that to be -2. We solve this equation, we can subtract 3. That's -2x equals -5. I'll divide both sides by -2, and that works out to be 5 over 2, which is 2.5. And this is our value of C, but before you finalize that decision, you need to remember that the value of C needs to be in the interval from 2 to 3. So if we think about our interval, we have 2 and 3, and 2.5 does fall in that interval between 2 and 3. So we found the value of C that is guaranteed by the mean value theorem. Thank you for checking out my videos. Have a great day.